Hi, my name is Adolfo Campos, and today we explain the experiment of the Bernoulli equation. Okay, so first we have to review what we have seen in previous experiments. As you may remember, if we assume that we have an ideal fluid and we are passing it through a tube that changes its area, its cross-sectional area, we get these two formulas, which are very important. First of all, that the multiplication of the area, the cross-sectional area, times the velocity of the fluid at one point is always constant. This multiplication always has the same value, and this value is called the rate flow, which is the change of volume divided by the change in time. And second of all, the pressure plus the pressure at one point plus half the density times the velocity squared at one point plus the density plus times the gravitational acceleration times the height at one point is always constant. We have seen these two formulas on previous videos, but today we're going to use to make a derivation using these two formulas. First of all, we need to have a tube that doesn't change its height, so therefore we can eliminate the term of height from this formula. Then, as you can see, we now have that the pressure plus half the density times the velocity squared is always constant along this tube. We can rename this constant as density as pressure total, which will be equal to pressure, which in this case is this P right here, plus PD, which will be all this term right here. This is called dynamic pressure, and is equal to half the density times the velocity squared at any point. Okay, so what if we want to calculate the change in pressure from one point to another, specifically the change in dynamic pressure? Well, we use this term, but we can replace the velocity with another velocity using the previous formula, the one right here, that relates area times velocity with another. Let's say we want to isolate the velocity at point 1, therefore velocity at point 1 is equal to area 2 times velocity 2 divided by area 1. And as you can see here on this formula, this is exactly what we have here. It's just everything squared because it was velocity squared originally. But as you may see, if we assume a reference point at point 2, which wouldn't change, we can say that the half is a constant, obviously, the density of the fluid is a constant, the velocity at point 2 is a constant because it's our point of reference, the cross-sectional area is the same, is also constant, and the only term in this whole equation which is a constant is area 1. So therefore, we can just group all of these into a constant called C, and see that the dynamic pressure at point 1 from a reference point 2 is equal to just some constant divided by the area 1 squared. So in this experiment, we're going to try to prove this formula and some derivations from it. So how we're going to do this? We're going to use this apparatus right here. This is basically a wind tunnel. How it's made is that here is a fan, which will rotate so that air goes this way. Air will enter from this grill and stay in this long area, volume, sorry. As you can see here, there are 6 points, A, B, C, D, E, and F. And as you can see here, there's a ramp. This ramp reduces the total volume and therefore the cross-sectional area at any of these points, and the cross-sectional area is also stated here on the re-experiment. And this is usually connected to this apparatus right here. We will tell us the velocity and pressure, but we actually connected it to a Pasco interface, so our measurements are more specific and in real time. So how we did the experiment was we made the wind turn in. We made sure that there isn't turbulence from any of the two ways. And first, using a probe, we measure the pressure at every of these points. First at point A, then wait 5 seconds for the air to stabilize again because the probe moved it. Then at point B, etc., etc. So what we measured was obviously the area, which is stated right here, and the pressure at any of these points. So here is the differential pressure and the area for each of these points. This is in pascals and this is in square meters. So as you may remember, we say that this formula says that the dynamic pressure will be equal to a constant divided by area 1 square. So therefore, if we make in a graph the pressure y and the area x, they should follow a pattern of y equal to a, which in this case will be constant, divided by x. We also added another term plus b, just so we get a more correct result and see if this will be actually 0, proving the formula. And here is our graph. As you can see, the points do follow this pattern, in which a will be around 0.01, but sadly there is some b, and it's a quite large b. But I would say this is due to the differential pressure right here. Also, you must remember that we're using air, and air is not a perfect fluid at all. It's somewhat compressible, it changes a lot, etc. So all of these formulas will only apply to an ideal fluid, and air is not, but we're just assuming that the formulas can be applied as well. So as you can see here, although it isn't exactly this relation that we wanted, the graph does follow a tendency from those points. So we can say so far this is correct. Then what we want to measure is the velocity. The velocity, we got it from this formula right here. Sorry. The velocity, we got it from the formula of the differential, that this formula right here, this one. This is the differential pressure is equal to half times the density times the velocity squared. While the density of air is known, it just changes due to the height, the altitude, sorry. So we just took the altitude of where the where experiment was made, which was on Cholula, Puebla, which is around 2,150 meters above sea level, and just calculated the air density, which will be around 0.95 pascals. Sorry, kilograms per square meter. Sorry. So as we already have the pressure, then we have all these values in order to isolate velocity. And with this velocity, we got with this formula, we got these data for velocity. So what we're going to try to do is to graph this function using the previous formula we saw in order to calculate velocity. And as you remember, area 1 times velocity 1 is equal to area to velocity 2 no matter what point. It's always a constant. So therefore we can isolate velocity 1 and just use this formula. But area 2 times velocity 2 will be a constant. Remember, this is the reference point we are using. So therefore, velocity 1 will only depend on area 1. So here, if we make velocity y, area x, and just some constant a, we get this this relationship, and as well we added some b in order to account for some possible errors. And as you can see here, this also follows somewhat closely this relationship, although a as well is very small compared to b, but I will say this is also because of the initial pressure that we started at. But as you can see here, it also follows the tendency of this formula. And finally, we wanted to get the flow rate. As you remember, area 1, well, any area at any point times its velocity is equal to the change of volume divided by the change in time, and this we call the flow rate, which will be RP. And this should be constant, well, theoretically, with an ideal gas. And we calculated it using simply this formula. We just multiply the area right here times the velocity right here to get the rate flow. But as you can see, it's not constant from this data. It is decreasing along with the area decreasing, but we will see how much exactly constant it is using a graph. So here is our graph. As you can see, we put the flow rate on the y-axis and area on the x-axis. Therefore, it will follow this pattern, just multiply by by the velocity a in this case, to get this tendency. And as you can see from the graph, it does follow that pattern, but sadly the slope is around 0.5. But because rate flow should be constant, this should actually be 0. So we weren't actually expecting a tendency like this, we were expecting a horizontal line. So this wasn't exactly correct. This can be for a number of reasons. First of all, velocity is not exactly another constant. As you saw previously, it's another. All of these values depend on each other. So therefore, velocity cannot be considered constant. Second of all, as I said previously, air is not an ideal fluid. So therefore, we shouldn't assume that these formulas will apply perfectly to it. And third of all, there could be any turbulence or a small error that we did that will change the rate flow. So sadly, we didn't get a static rate flow, but at least we proved that some of the derivations agree with experiments, even if it isn't an ideal fluid we experiment in it.